Hello everybody. Today we'll talk about how do we convert spectrograph to octave bands. Now when you acquire sound data, it's important to view it in the frequency domain so as to understand what the sound is really made up of. You can perform an FFT analysis which will result in a spectrograph, or you can perform an octave analysis which will result in octave bands. Now both spectrograph and octave bands are literally conveying the same information but in different forms, and sometimes it may be necessary to convert one result to the other. So what is a spectrograph? When you acquire a sound signal and perform FFT, you're going to get a spectrograph. The y-axis is the sound pressure level. In this case, it's the dB full scale, but it can also be the dBA scale. And the x-axis is the frequency. It spans from 20 to 20 kilohertz because that is the human audible range. And here we can see, some spectral lines at 1 kilohertz and 2 kilohertz. Now an octave band is also the same thing. The y-axis is still the sound pressure level, and the x-axis is still the frequency, but rather it's not complete frequencies, but rather octave frequencies. So as you can see here, there are some numbers: 31.5, 63, 125, and so on up to 16K. So those are the octave bands. So this is the first difference between spectrograph and octave bands, is that you see lines here, spectral lines, and you don't see lines here, but you see bands. Now let's talk some basics about octave bands. The first is the center frequency. So center frequency next is 2 power 1 by n times center frequency previous. Now the n represents the resolution of octave bands. If we're considering 1 by 1 octave bands, n equals 1. If we consider a higher resolution octave band, for example 1/3 octave band, n becomes equal to 3. We'll stick to 1 by 1 octave bands because it'll keep the calculation simpler. And so if you plug in n equals 1, you get CF next is 2 times CF previous. Let's check it out here. So let's say this is the center frequency, 2000, and this is the next center frequency is 2 times the previous center frequency. So 2000 is 2 times 1000, and this holds true everywhere. So 1000 is twice 500, 500 is twice 250, and so on and so forth. The next is the upper and lower limit frequency of each band. So CL is CF times 2 power minus 1 by 2n, and n is again equal to 1 because we're interested in 1 by 1 octave band, and you get this relation between the lower limit and center frequency and upper limit and center frequency. So pictorially you can see something like this. So in the screen you have this 1000 hertz as center frequency, and on the right you have this upper limit frequency, and on the left you have the lower limit frequency. So you can compute that using these equations. In fact, I've computed it for all the center frequencies from 31.5 to 16,000. And these are the respective values, the lower limit and the upper limit. So which means that what does this lower limit and upper limit means? That this frequency of 31.5 comprises, this band comprises of frequencies from this to this. And this holds true for each and every band. Now, if you want to learn more about octave bands in detail, like octave 1 by 1, octave 1/3, or higher resolution, please check the relevant links in the description below. All right, so this is a test tone that I've created. The composition frequencies are displayed here from 25 hertz to 11,500. So this is a test tone I created so as to perform an analysis as in spectrograph analysis and then convert it into octave bands. So you can listen to this tone first. So first we perform a spectrographic analysis, simply, perform the FFT, and we get a result something like this. So on the y-axis, I have the sound pressure level in dBA scale, and on the x-axis, I have the frequency from 20 to 20 kilohertz. So first step, we acquire all the data. So we know the frequencies from 25 hertz to 11,500, and we acquire the sound pressure level at each of those frequencies. We will restrict to 1 decimal places, and these are the values that we get. Second, we segregate the frequencies. Now, we do know the range of the octave bands. For example, 31.5 band spans from 22.3 to 44.5. So we know all the values for each of those octave bands. Now we're going to segregate the frequencies. For example, we know what frequencies are present here, and we're going to start, segregating the frequencies that fit in within this particular band. For example, 25 hertz and 30 hertz fit within this band, and 100 hertz and 150 hertz fit within this band. So we do that for every single band, and we can start accumulating frequencies that actually fit within the octave band range. And the next step is to perform logarithmic addition, which is, now we know that 25 hertz has some sound pressure level value, and 30 hertz also has some sound pressure level value. But then we have to represent these two frequencies as one band, which means we have to add them up. But we cannot simply add them up arithmetically. We have to add them up logarithmically. So that's where the logarithmic addition comes into play. So just quick basics about logarithmic addition. If you have two sound pressure level, S1 and S2, the total sound pressure level is given by this equation. So you just plug in the values. For example, let's say we have 53.6 and 55.9. Simply plug in the values here and you're going to get something like 57.9 dBA. If you want to learn more about logarithmic addition as well, please check the link in the description below. So we perform the logarithmic addition for each of those frequency bands and then compute it, and we get something like this. So we have logarithmically added, for example, in this case, 25 hertz and 30 hertz and so on and so forth for every single octave band range. So we're all set. So now the last thing to do is simply plot. Now we know that, what is the center frequency of each of those octave bands, and simply we're going to plot it and get the octave spectrum. So now each band is actually composed of two or more frequencies, and that's it. This is the representation of the octave spectrum, 1 by 1 octave spectrum. Now you can actually extend the same concept to higher resolution octave bands, such as 1/3, 112, 124, and so on. And higher resolution just means more data. The only difference is going to be the calculation time. So as you can see here, even 1 by 1 was pretty calculation intensive. So 1/3 will be like more calculation intensive because you have more bands. But the concept is still the same. You can extend it to any number of higher resolution of octave bands. All right, thank you for watching this video. I hope you enjoyed it. Have a great day.